All right, so our big theorem of this chapter is at the top of the page, that a number alpha is constructible, that's a constructible length that we can make with a compass and straight edge only, if and only if alpha is an element of some subfield of R that's built out of Q and adjoining the square roots at every step of the way. The corollary to this says, if real number alpha is constructible, then first of all, it's algebraic. Okay, and then second, its minimal polynomial over Q has degree 2 to the I. You're going to prove this corollary for a homework assignment, but the way we're going to use it is actually the contrapositive of the way it's stated. So reframing this, we're going to say if alpha is not algebraic, or if the minimal polynomial is not of degree 2 to the I, then the number alpha is not constructible. And so we're going to be able to use that to prove some impossibility theorems. So the first one, this one is talking about it being impossible to construct the side of a square whose area is equal to that of an arbitrary circle. This one is sometimes called squaring circle. Okay, and so this theorem says it's impossible to square the circle. And we're going to prove this using that restatement of the corollary above. So our proof is going to be, if we could do this, we could construct the length of the side of a square whose area is equal to the area of a circle of radius 1. Okay, so circle of radius 1, the area of that circle is pi times r squared, which is 1 squared. So the side length of a square would be root pi. Okay, if we could construct root pi then we could construct root pi times root pi, because we knew how to do, if we could construct a and b, we could construct the product a times b. And so if we could construct root pi, we could construct pi. But we know pi is not algebraic. Therefore, it's impossible to square the circle. Okay, so just using all the tools from the algebra that we learned, we proved that it's impossible to square the circle, to construct a square whose area is equal to a circle that was constructible. All right, oops. Next one, we're going to do one more impossibility theorem here. So this time we're going to be constructing the side of a cube whose volume is twice that of a cube. So this one might be referred to as doubling the cube. So this theorem is saying that it's impossible to double the cube. And so again, we're going to do this kind of with example by saying that, so the theorem says we can't do this for an arbitrary cube. And so we're going to say, if we could do it with an arbitrary cube, then we could do it with a cube of volume 1. So if we could do this, we could construct the side of a cube whose volume is double that of a cube of side length 1. Okay, because I know I can construct a unit length, I just decide what my unit length is. So a cube whose side length is 1, the volume is 1, and so to construct a cube of volume 2, we need side length cubed root of 2. But the minimal polynomial over q of the cubed root of 2, that minimal polynomial is x cubed minus 2, which is of degree 3, contradicting our corollary. And so thus, it's impossible to double the cube. Okay, so the structure here is we say, if I could double the cube, if I could double the volume of a cube, I know I can construct the side of a cube of length 1. So I would need to make a volume 2 cube. I'd need to be able to make the side length of that, which is cubed root of 2. But minimal polynomial has degree 3, which doesn't agree with our corollary above that said if the minimal polynomial is not of degree 2 to the I, then the number is not constructible. Okay, so we've proven two results, that it's impossible to square the circle and that it's impossible to double the cube.